Now we'll look at something called the perpendicular bisector lemma. If M is the midpoint of line segment AB, and the distance from P to A is the same as the distance from P to B, M is different from P, then the following. Before we fill in the blanks, let's draw a picture. So I have a line segment AB, and I have the midpoint. We'll call that M. Okay, and they're saying that P, the distance from P, I'm going to draw P somewhere, such that PA is equal to PB. So you may figure out that P is going to have to be like, as an example, right there. Call that P. And it looks like I've got those two line segments being the same. Well, what do we know in this case? This line PM will be what is called the perpendicular bisector of line segment AB. So PM is perpendicular to AB. And again, that's because the point P is the same distance from A as it is to B. And then this line PM bisects which angle? This line M, a line PM. It's bisecting this angle right here. My drawing's not perfect, but something like that. These two angles here will be congruent angles. So it bisects APB, the angle APB, or you could write it BPA if you like. Perpendicular bisector lemma. Okay, the next one is a theorem, perpendicular bisector theorem. It's kind of a generalization of this up here. I'm going to draw this line segment again way over to the left because I need room over to the right for the next, for number 9. This is A, B. The set of all points that are equidistant, the same distance from distinct points A and B is the perpendicular bisector of AB. So one point that is equidistant from them is the midpoint, right there. All the other points are going to be on this line, similar to the picture we just drew a minute ago. So if you take all of the points that are the same distance from A and B, you get the perpendicular bisector of the line segment AB. So any point you choose would give you an isosceles triangle because this distance is the same as that. All right, now the last thing we're going to look at is a theorem. We're going to prove it, but most of the proof is done for us. Prove the following theorem. The perpendicular bisectors of the sides of a triangle, if two of them meet, are concurrent at a point, which means they meet at a point, they intersect at a point, that is the center of the circle, called the circumcircle, passing through the 3 vertices of the triangle. The point of concurrency where they meet is called the circumcenter of the triangle, the center of this circle we're talking about. Okay, well, let's start off, figure out what we're doing. Let's draw a triangle. I'm going to try not to draw an equilateral or maybe even isosceles. I'm going to draw a triangle A. Let's see, AB will be one side. And then maybe something like that. And like that. All right, I hope I have enough paper here. Oh, this is just a note. And something that will, in absolute geometry, talk about that later. It's possible that this highlighted condition is not true. In other words, in this case, they will always meet, but in absolute geometry, two of those lines may not meet. We'll see that later. Okay, so what are they saying? Let's take a perpendicular bisector of this, of AB. So perpendicular bisector of AB would be something like this. Right? That's a 90-degree angle. Now let's do it with one other side. Maybe that looks too easy. Let's try this one. Do a perpendicular bisector of this side. Well, not exactly what I wanted. I did not mean for these 2 points to intersect right about there. But they could have intersected outside of the triangle. And maybe when you draw it, it does. So this is the circumcircle. What we have now is that with this point, the distance between this point and B, and the distance between this point and A, and we're going to draw the circle. So if I were to draw the circle, this is going to be terrible. Well, let's do the proof first, because that'll kind of explain what the drawing is going to look like. Circle looks something like that. Get that over with. Okay. It turns out that this point, since it's the intersection of two perpendicular bisectors, turns out it's going to also intersect with the other perpendicular bisector. All three of them will pass through that. So let's do the proof. Suppose perpendicular bisectors of AB and BC, that's the ones I drew up here, meet at point O. So this is going to be O. Since O is on the perpendicular bisector of AB, we know by the perpendicular bisector theorem that the distance from O to A is the same as the distance from O to B. By similar reasoning, the distance from O to B is the same as the distance from O to C. And by transitivity, if OA equals OB and OB equals OC, then OA is equal to OC. Hence, O is the center of the circle that contains the three corner points, or the three vertices, of the triangle ABC. That wasn't my picture. I should have made the triangle maybe skewed a little bit more so that this point was even outside of the triangle. But it works every time. And as a comment, I already said this, the point O actually lies on the perpendicular bisector of all three sides.